name is Nathan Wiatrek. I am a research engineer down at Southwest Research Institute in San Antonio, Texas, where I focus primarily on flight software, which is perfect for this. Today I'm going to be talking about an ARM processor for spaceflight mission reusability. First up, a tiny bit about SwRI in case you haven't heard of us. We are a nonprofit research and development organization. We've been around for over 75 years. We have almost 3,000 employees, almost 1,500 patents, and we have a very wide breadth of technical know-how. This ranges all the way from deep sea, into what we're talking about today, which is deep space. So what am I going to talk about? I'm going to talk about why we should actually care about processor reusability. I'm going to talk about the current state of processors. I'll refer to them a lot as legacy processors. I'm going to talk about this specific ARM processor's advantages. I'm going to talk about benchmark results and comparison between the current processors and this ARM processor. And then I will talk about what is next. So why should we actually care about processor reusability? Well, each mission has a different goal in mind, and we want to be able to meet all of these separate requirements. Sometimes we have a really long mission that has a big swap constraint, and since it's going to be running for so long, you have a very tight power budget. Other times you have a complex task that you need to be running on, and maybe it's only running for a few months, and so you can kind of push that computational envelope and you don't really care about your power consumption. But as new missions are coming up, more and more requirements are on the computational side to get things done quickly. But not only from requirements, we also care about getting our software to the hands of its users. We want to be able to develop software faster so that way we can see the mission succeed. And having a consistent hardware platform that meets varying requirements would be really great, so that way we don't have to have constant context switching, and we can write highly optimized code once. Basically, think of it, write once. You don't have to reinvent the wheel for every driver that you've ever done. And finally, we care about processor reusability because of flight heritage. Because it's so expensive to put a processor up in space, and it's a very harsh environment, we need to make sure that this processor is going to work once it gets up there. So having something that can meet varying requirements, can be reused and give you a lot of flexibility, and also has flight heritage is kind of a no-brainer. So where are we right now? Well, I'm going to bin the current processors that we're using into three separate buckets. We have your high-performance processors. These are going to be your workhorses. They're going to get you your task done as quickly as it can, but they also have the drawback of they're going to consume a lot of power. Next up, you have your standard 32-bit processors. These are still kind of clunky by our standards, but they're still going to get the task done for you. It'll be a little bit slower than your high-performance processor, but on the other hand, they're going to consume far less power, which is a big benefit. And then finally, you have the low-power processors. These are the guys that are giving you pretty low performance. We're talking 2 to 200 DMIPS running at 100 megahertz. And their big benefit is the fact that they don't consume a lot of power. But these are basically 20-year-old processors, and they kind of lack the flexibility to meet varying requirements. You can turn on cores, but you can pretty much only do that once, set the frequency, but you can pretty much only do that once while you're down here on Earth. And we often trade what the processor can actually do for the reliability and design of the system, which is really important to know. And we also configure the processor to either address the most computationally intensive or the part that's going to take and consume the most amount of power. Sometimes those are the same thing, but sometimes they're not. If you have a budget of, hey, I can only take 1.5 watts of power, then you're going to find the thing that draws the most power, and you're going to scale down to where that's exactly what you're drawing, so you never go past that budget. And that's obviously not where we want to be. We want to be doing things that give us more energy efficiency, give us a lot of flexibility. So let's go ahead and talk about the ARM processor. So this specific ARM processor is power efficient and high performant. I will prove that to you in just a few minutes, don't worry. It features a 64-bit quad ARM core that can run up to 1.8 gigahertz. It has ECC protected L1 and L2 cache, and has a few security features such as implementing a trust architecture like Secure Boot, which gives you cryptographic checks along every stage of the boot process. And it has a SEC engine for offloading things. So think of your basic encryption standard, your advanced encryption standard, your RNG number creation. All of that can be offloaded to just that engine. And it gives you dynamic power management features. It gives you that finer tuning of power utilization, which can give you a lot more platform usability because you can meet a lot more. So let's talk about the legacy processors. So here are 3 processors that I'm going to be talking about. These are all currently being used. We have the GR712, the UT699, and the MPC8548. For the first part of this talk, I'm going to be talking about specifically synthetic benchmarks. Those are drystone, whetstone, and Cormark. Everyone's pretty used to these. They're very good for determining relative performance in a lab situation. So let's go ahead and look at some of the results. So up first, we have the GR712. It is a dual-core processor running at 100 megahertz and draws 1.5 watts of power. Congratulations. It scores on the Cormark, which is what I'm going to talk about mostly because that's the least optimizable away, at 1.86 Cormarks per megahertz, which is good. We have the MPC8548, which is a single-core processor that runs at 15 times the frequency as what the GR712 did. As such, it consumes almost 10 times the amount of power. And all that's giving you is just 2 times the Cormark score. And then finally, you have the UT699 running at 66 megahertz, which consumes the least amount of power, which intuitively gives you the least amount of Cormarks per megahertz. So let's talk about how the ARM processor actually did. So this is a graph of the Cormark score. It's pretty much exactly what you'd expect. Hey, the higher frequency, the higher number of Cormarks you'd get. Since Cormark is a multi-threaded application, at least this implementation was, turning on more cores gives you more Cormarks. So everything is looking good there. Up next, we have drystone and whetstone. It's also pretty consistent. This is a single-threaded application, so having more cores on basically changes nothing, which is why those lines are very stacked. And so running all of the cores on at 1600 megahertz, we get almost 40,000 Cormarks, almost 8,500 DMIPS, and slightly above 2,000 MWIPS. But if you recall, what I just showed you were not the raw numbers. They were in terms of per megahertz. So let's look at the performance there. And you can see at 4 cores on, we blow everything out of the water. Compared to the MPC8548, which was the highest performing processor, we are 6.5 times better than that. That's with 4 cores on. As we reduce the number of cores, of course, our Cormark per megahertz goes down because it's multi-threaded. But even with just 1 core on, we're blowing all of the competition out of the water. So we're getting 6.5 times the highest performing legacy processor there. Up next is drystone and whetstone. You can see again that the ARM processor is beating the GR712, which was the best performer for DMIPS, which had just over 2. We're getting over 5. With MWIPS, everything was just above 0.2 per megahertz, and with the ARM processor, we're getting above 1.2 MWIPS. Now, I know what you're thinking. That's great. You have a very computationally intensive processor, but it's probably drawing a ton of power, and you haven't solved anything. Well, let me assuade you of that. So with all cores on running at the max speed that we could get this kit to go to, we're only using 5.7 watts, which is significantly less than the 14 watts that we were getting with the MPC8548. And running it down to the lowest speed we could run on with also having only 1 core on, we are using less than 40% of the power of the MPC8548 while still beating it in those Cormark scores. Now, further research is actually needed because we think we can get those 2 numbers down lower. Well, really the 4.5 watt one down lower. We just have to look at some more board configuration and do a little bit more dynamic power management. So up next is the power characteristics for all the synthetic benchmarks. not just averaged out. So you can see the core mark, everything is going up as you increase the frequency and you increase the cores on. This is also basically true for dry stone and wet stone. They increase pretty much exactly how you would expect them to. So let's go ahead and change from a synthetic benchmark to a closer to real world benchmark. Synthetic benchmarks are great in a lab scenario, but they're not really indicative of what your processor is going to be doing in the real world. The reason that this is a closer to real world instead of a real world application is we are not currently running our algorithms that we have on our satellites on this processor. We chose two different categories, image processing and machine learning. These are either very relevant or are kind of up and coming, as we're seeing in this conference. I would like to note that we are only going to be talking about the ARM processor and the MPC 8548. We couldn't meet the same power level consumption that the GR712 and the UT699 did. So it's not really fun for us to say, hey, we can destroy you on all of these performances, but we can't actually meet your power requirements. So first up is JPEG LS compression. So JPEG LS stands for JPEG lossless, and it's a lossless data compression technique. That's a requirement of a lot of space missions. If you're taking pictures, it's really important that you get all of the data back down to Earth. So what we did is we encoded and decoded an 8 megapixel image, ran this several times, and we averaged out the numbers. And here are the results. So the MPC 8548 took over 8.5 seconds to encode this 8 megapixel image, whereas the ARM processor did the exact same thing in less than half a second. The MPC 8548 had a similar story with decoding, where it took a little over 8 seconds, where the ARM processor took about 360 milliseconds to do it. This is a speed up of about 20 times. We expected it to be better based off of the 6.5 times on core marks, but we didn't really expect it to be this good. So we went in and made sure, did a point-to-point comparison of the pre-encoded image, the encoded image, made sure that the data file size was the exact same because it's the same algorithm, and then did a point-to-point comparison of the decoded image. And we found out that, hey, this 20 times speed up wasn't because we were only doing a 20th of the work. And then up next, we have the machine learning performance. If you don't care about machine learning performance, just know that this is a highly intensive operation, and so it's still important and shows you, hey, how good is this processor at doing something that takes a lot of time. Some different uses are mission planning or data collection. We've seen other things throughout this conference. But the focus area for our problem was object detection and classification. We use the MobileNet single shot detector. MobileNet is kind of optimized towards edge devices, and we utilizes EE-NBC's MLMark benchmark to help with harnessing and running these tests. So here are the results. We measured 3 different metrics. We had accuracy, throughput, and latency. Throughput is exactly what you think. It's how many inferences can we get through in a given time. This is measured in frames per second, and basically higher number is better. We have latency, which is how long does it take for an inference to be done, and lower is better. However, a note here is that this latency value is actually the 95th percentile. So 95% of the time, your number will be better than what's measured here. So this is almost a worst case scenario for you. And accuracy is slightly more complex because it's a 2-phase thing, but it basically comes down to how close was your bounding box to the true bounding box versus, and did you classify the object correctly? So if it was a dog, did you say it was a dog or did you say it was a cat? And compared to not only that, we use 3 different backends for this. We use the ARM and N backend, which makes a lot of sense because we're using an ARM processor. We had TensorFlow Lite, which is the, again, more edge device optimized version of TensorFlow, running at 32 floating point and 8 integer. And compared to other processors kind of in the same class, we found that we had equal accuracy, higher throughput, and lower latency. So these are, again, embedded devices. If we ran this on a GPU cluster, clearly that would destroy everything. So in summary, this ARM processor provides you enhanced computing performance, it gives you reduced power, and that gives you increased reliability and greater flexibility. And those four things are exactly what makes a processor reusable. And having those things give you superior optimization because, again, you don't have to reinvent the driver you've written 30 times already because you keep switching processors. You can have just a focused area of optimized one time and then just reuse that optimized library for this architecture. And that will ultimately help you with reducing project time and cost because you don't have to spend development cycles on optimizing. You can just reuse what you have. And hopefully that lower power will give you an extended mission lifetime. So what all applications can be used for this? Well, we have spacecraft command and telemetry, obviously big importance. We can do payload data processing with it, ultra low latency telecommunication, image processing and compression. We specifically showed that with the JPEG LS. Onboard decision making, including AI. We again showed that with the MobileNet single shot detector, as well as edge computing. So what's next for this area? Well, we know based off of some data sheets that this is a rad tolerant processor in a certain configuration, but we want to see how is this going to react when we're running heavier algorithms on it. How often does it fault? We need to know all of those things before we can really be confident in this, because that's an area of research that we're going to be doing. We want to evaluate additional dynamic power management features. So like what I was saying earlier, we think we can get those numbers lower. And so we want to be able to get those numbers lower to meet more low power systems to kind of fight the GR712 and the UT699 at their power budgets. And ideally, lowering the power will give us a little bit mission lifetime extension. Finally, we want to investigate the security features for use in space application. There's a lot more security requirements going on satellites, whether that be your uplink, your downlink, or anything in between. And so it'd be nice if we could ensure that, hey, this processor meets all of that and can ideally throw some of this off to the SEC engine. So with that, I would like to thank the Flight Software Workshop for having me, and I will now be taking questions.